Hello, I'm Tasha Dupre, the Interim Dean of the College of Sciences at the University of Central Florida. We'd like to thank you for joining us for our virtual launch break space talks hosted by the UCF College of Sciences and the Orlando Science Center. We are excited to partner once again with the Orlando Science Center to bring you fascinating insight into the cosmos from faculty in our college and educators from the Orlando Science Center. We'd also like to encourage you to visit the Orlando Science Center and tour the amazing Planet Pioneers traveling exhibit firsthand. The exhibit will be on display during the Orlando Science Center's normal business hours from now through May 9th. Now I'd like to turn it over to Spencer Jones from the Orlando Science Center as he will introduce our speaker and be our moderator for the talk today.
Hello everyone. Welcome to this awesome collaboration that we have with UCF and the Orlando Science Center. My name is Spencer. I'm over here at the Orlando Science Center right now. I'm super excited to be hosting or moderating this talk that we have going on here today. We're going to be highlighting some awesome research on the UCF side. I mean, like literally awesome as in awe-inspiring. I mean, the stuff that we're talking about it just makes me super excited. So I'm excited to jump into it. But before we get there, I do want to mention that we're also highlighting the Planet Pioneers exhibit that we have going on at the Science Center right now. It's a traveling exhibit. If you don't know, a traveling exhibit is one that is literally just that. It's an exhibit that travels around the country. And right now we have an exhibit all about exploring other planets and moons with robots and humans. And it's really, really cool. I'm biased because I personally love space, but a lot of our traveling exhibits involve a bit more kid-friendly stuff. They're more family-friendly, but this one really is for all ages. There's a lot of things in there that even I struggle with a physics degree who's worked here for 5 years. So if you're at all interested in outer space, I recommend coming to the Science Center. Like we said, the exhibit closes on May 9th and it'll be gone forever. So definitely make your way over here to check out Planet Pioneers. And before we pass it over to our speaker as well, I do want to mention that check out the Q&A field. If you have any questions during the talk, please do ask as many questions as you want. We'll get to as many as we can at the end of the talk. And if you don't get to all of them, if we don't answer all your questions, there's going to be other ways to talk to our speaker as well. And make sure you upvote questions that you like so that we can bump those to the top and make sure we focus on them. So without further ado, I do want to pass it over to our speaker today. His name is Dr. Joshua Caldwell. He is a Cassini Co-Investigator, a Pegasus Professor, and Associate Chair of the UCF Physics Department. So please, Josh, take it away.
Thank you, Spencer. Very happy to be here and talk about Cassini, a mission that is near and dear to my heart. I frequently refer to Cassini as the mission of a lifetime because I worked on it for 30 years, and people assume that it's, when I talk about it, they're assuming that I'm referring to my lifetime. But here I am with my daughter, Ilea, in 1990, when I started working on Cassini as a freshly minted postdoc. And at that point, the mission was in its design phases. It was just drawings on paper. Here she is, 8 years old in the wee hours of the morning of October 15th, just down the road at Kennedy Space Center to see the launch in 1997. And then 8 years later, 1 year after Cassini arrived at Saturn, she was in middle school, actually high school at that time. And then at the end of the Cassini mission, after 13 years in orbit around Saturn, she accompanied me to say farewell to the spacecraft, an event where I readily admit I shed many tears. And just 2 weeks after that was her wedding. So it was really the mission of her lifetime. It was a lifetime spanning mission and a very remarkable one. It's what NASA calls a flagship mission that had very broad goals to study everything about Saturn and its system. I've got a note that you're not seeing my beautiful slides. So let me go back again to that and try here. I'm sorry about that. Thank you for the notes. I won't tell my story again, but I have to show my beautiful daughter. There we are at the end of the Cassini mission. And 2 weeks later, her wedding. So it was a lifetime long mission to Saturn. And here is the spacecraft itself. It's what NASA calls a flagship mission at the time, and I believe it's still true to this day. It was the largest interplanetary spacecraft that we had sent off to another planet. It was about the size of a large SUV. You can see the people there. For scale, it had a dozen instruments on the orbiter, and then it carried a European-built probe that descended into the atmosphere of Saturn's largest moon, Titan, and landed on the surface and collected a lot of interesting information, which I'll talk more about in a little bit. So the Saturn system is a very large, complicated, dynamic system. It has a lot of moons, 62 moons that have been identified. The ring system would sort of comfortably fit in between the Earth and the moon, and that's just nestled right in the center of the overall system. And so this mission had the goal of studying all of these objects, not just the rings, not just Saturn, not just Titan, but all of these objects. And to do so, when you're flying around, requires getting lots of different points of view, lots of different perspectives on the planet and the rings. If you're flying around to look at the moons, you're going to be in the ring plane and you can't see the rings, and so you have to change the orbit. So this video is showing the initial 4-year mission. The orange curve is illustrating the path that Cassini followed in that what was called the prime mission. So when it was launched, it was designed to last for 4 years. And those various other circles and ellipses there are illustrating some of the key moons of the Saturn system. And Saturn and its rings are right in the center of that whole system. And all of this flying around the Saturn system primarily used the gravity of the moon Titan to change the trajectory, to change the orbit of the path of the spacecraft, and to use very little fuel to do so. So it would fly by Titan many times, and in each one of those flybys, you can see in the lower right-hand corner, it would point its radar towards the surface of Titan, which is encircled by a global haze layer, which makes it very difficult to get photographic images of the surface from space, and do radar mapping of the surface as well. So this whole process of figuring out what would be done during that mission took the years that we spent designing the spacecraft and the 6.5 years that Cassini spent flying from Earth to Saturn, so that all of the observations could be planned down to the minute, and we can make the best use of that time and capture images such as the stunning picture that you're seeing here, which I include only for its visual effect. The stripes that you see here on Saturn is the shadow of Saturn's rings cast onto the planet, and you can imagine that that's a phenomena that we don't get here at Earth, and it can have effects on Saturn's weather. And as Saturn goes through its seasons, those shadows move from one hemisphere to the other, and at the equinoxes disappear nearly altogether. My particular area of research focuses on Saturn's ring system, and so I'm just giving a little bit of a geography lesson here. For Saturn's rings, they have the incredibly poetic names of A, B, C, D, E, F, and G. E and G are not visible in this particular representation, but the main rings, the ones that you see if you look at Saturn through a telescope, which I strongly encourage everybody to do any chance you get, and we provide that opportunity at the UCF Robinson Observatory during the academic year, are the A, B, and C rings. Those are the main rings where most of the material is in Saturn's rings. And we sort of think of Saturn's rings as a collection of snowballs. They're relatively clean snowballs, they're relatively bright. The sizes of those particles in Saturn's rings are small, ranging from sort of the size of a marble up to maybe the size of a large car or even a house in some cases. And I use the analogy that if wherever you are right now, if you imagine converting everything around you, a chair, laptop, books, utensils, into an equivalently sized snowball, and then let them float around in the room with you, well, that's kind of what it would be like to be in Saturn's rings. And those particles bump into each other very, very gently and very slowly. And when they do so, they bounce off each other instead of sticking together. And the reason for that is because Saturn nearby is exerting its own force on those particles that prevents them from sticking together, which is why we have rings close to the planet and moons further away. This picture here is just showing some of the very complicated and so far unexplained structure in Saturn's rings. You can see that bright region has a sort of straw-like feature, and that's a complete surprise because we would expect all these particles to just sort of like line up like cars on a racetrack and not give us these sort of clumpy features showing up, which ties into one of the reasons that we study planetary rings in the first place, which is they're kind of similar to what you would see if you went to another star that was just born and had planets forming around that star. There would be a disk of particles, and those particles would be colliding with each other, and we would be seeing some of those particles stick together to form larger and larger particles and eventually make planets. In the rings, we have that disk kind of locked in place by Saturn's tides so that the moons aren't forming within them. At the same time, we do actually see some intermixing of moons and rings in Saturn's rings. So in this picture, right at the center, there's a bright white dot, and extending up and to the left at sort of the 11 o'clock position, you can see a dark line, and that line is the shadow cast by that bright dot. And by knowing where the sun is and measuring the length of that shadow, we can figure out how big that object is that's casting that shadow. And it turns out it's about a half a mile out of the ring plane. And the rings themselves are only a few meters thick. So they're as big as from the Earth to the moon across, but in thickness, they're only about the size of a 1 or a 2-story building. And so if you imagine this very, very thin layer of snowballs racing around Saturn, but very gently jostling into each other, and then you would come across this literal mountain of ice and snow in the middle there. Where did that thing come from? How did that happen? Well, we have other clues and other observations that there are big objects lurking within the rings. These 3 images show objects that are referred to as propeller objects because they are boulders that are invisible here, but are stirring up the orbits of the snowballs that are orbiting in Saturn's rings around them. And they produce this sort of characteristic 2-bladed appearance here. And we've seen dozens of these objects in Saturn's rings. So it's telling us that in spite of Saturn's best efforts to keep the ring particles apart, some of them are managing to stick together. And that gives us some clues about how the early stages of planet formation may have occurred. I'm going to show you right after this cartoon a picture of a moon where we can actually really see the moon very well orbiting within Saturn's rings. And as the moon is sort of like a giant ring particle, or you can think of the ring particles as really, really tiny moonlets. And they're all orbiting Saturn at different speeds. The closer they are to the planet, the faster they go. And so you've got like a fast lane and a slow lane. And when the particle passes in the fast lane, passes a moon in the slow lane, the moon's gravity gives that particle a little bit of a kick and causes it to go on a different shaped orbit. And you can see here the moon Daphnis, which opens up a little gap in Saturn's A ring, That gap is about 20 miles across, about 30 kilometers across. The moon is just a little bit smaller than that. And you can see these lovely waves and ripples on the edge of that gap that are caused by the gravitational interaction and perturbations between the moon and the ring particles. More distant moons are also interacting with the rings, and they produce waves. And so many of these stripy features that give the rings a kind of a record groove appearance are caused by gravitational kicks that are received from some of the moons that I'll show you pictures of in a moment, that cause a periodic oscillation in the orbits of the ring particles, which produce waves. And it has both slinky waves, like if you took a slinky toy and sent a pulse down it, some of these waves are like that. There are also warping or bending waves in the rings as well. And some of those waves are even caused by things going on inside Saturn, which we'll get to in just a few minutes. Here's now a picture of another moon in a gap in Saturn's rings. You can see that dot, and you can also see it's casting a shadow. That narrow dark stripe off to the left is actually the gap where that little moon Daphnis is located. Here we're seeing Pan, which is in a much larger gap that's about 200 miles across, about 300 kilometers across. And here are three of these so-called ring moons, which have a very remarkable appearance. You can see on the right, Pan sort of looks like a piece of ravioli. It has this ridge of material on its equator, and that material is ring particles that have stuck to the edge of this moon that's orbiting in a gap in the rings. Daphnis, you see it to scale below, and you can see how small these moons are. They're sort of city-sized objects. And Atlas, which has this sort of very soft appearance, that's not blurriness of the photo, that's, you know, a very highly resolved image of that moon. It's also been accreting small icy particles from the ring system around its edge. So we have this interrelationship between moons and rings, and we see some ring particles sticking to moons and making them bigger, and evidence for moons that are within the rings. And it's possible that things kind of went the other way too. So this is Mimas, sometimes famously referred to as the Death Star moon for obvious reasons. And the object that made that big crater on Mimas, if it had been about twice as big, it would have shattered this moon. And it's possible that something like that happened to a moon that is now long lost that created Saturn's rings in the first place. 30, 40 years ago, we all assumed that Saturn's rings were left over from when the planet formed, and that they've been around and relatively unchanged for 4.5 billion years. But Cassini has revealed that the rings are very active, that they're changing on short time scales, and that they're not as massive as we thought. I'll tell you how we figured that out, all of which suggests that the rings may be less than 100 million years old, which for astronomers is just a blink of an eye, which means, you know, some dinosaurs, if they had managed to develop a telescope, might not have seen Saturn's rings if they had been inclined to look. I just want to share a couple of more of the odd moons at Saturn. This one, Hyperion, sort of looks like a sponge. Its craters give it an unusual appearance. Here's another moon, Phoebe, that's the same size as Hyperion, and it looks completely different. And it has to do with the fact that Hyperion, which looks like a sponge, probably is sort of spongy in the sense that it's got a lower density and is more porous. But one of my favorite moons is Enceladus. Enceladus is about the same size as the Death Star moon, but it looks nothing like it. And why is that? It's because Enceladus is an active, geologically active object. There is some stretching of this moon that is occurring due to tidal forces, just the way that our own moon stretches our oceans and causes the oceans to slosh up and down the beaches. Other moons in the Saturn system are pulling and stretching this moon, Enceladus, enough to give it a subsurface ocean of liquid water. And that subsurface ocean of liquid water is erupting through vents at its south pole, which you see in this picture here. So south is at the top. And you see these hundreds of geysers of water erupting through these vents and immediately crystallizing into little tiny crystals of water ice. And these particles end up going into orbit around Saturn, and they make Saturn's E-ring. And underneath, maybe we don't know exactly how far, but probably only a few kilometers to maybe 10 or 20 kilometers below the surface of Enceladus, there is a global sized ocean of liquid water. And Cassini was able to fly through these plumes of water ice and sample them and measure their composition on a number of times and see the other elements that are mixed in with those ice crystals as well. And that is one of the reasons why Cassini's mission ended the way it did, which I'll come to in just a minute after we take a look at the largest and perhaps most fascinating moon at Saturn, which is Titan. Here you see a panoramic view that was taken by that lander that Cassini carried with it to Saturn that was built by the European Space Agency. You can see in the center some sort of tributary river networks, mountains and low areas and mountain ranges. And it definitely looks like river banks and beds, but it's far too cold for water to exist in a liquid state on Titan. Instead, the substance that sort of fills the role that water does here on Earth at Titan is methane, or natural gas, the stuff we use for our backyard barbecues. Acts as a liquid, or sometimes it's a solid, and sometimes it's a vapor on Titan, just as water here on Earth is sometimes a water, sometimes a liquid, sometimes a vapor, and sometimes a solid. So you have rain and rivers of natural gas, methane mixed with ethane on Titan. And in fact, we can see the reflections, the glints of sunlight off giant lakes of methane and ethane near the poles of Titan in this infrared image that's able to peer through Titan's global haze layer. And Titan itself also has a subsurface global ocean of liquid water. It's far deeper than Enceladus's. It doesn't have direct access to the surface like Enceladus's geysers of water that are sort of snowing down over the surface and giving it that nice, pristine, crater-free appearance. But methane is an organic molecule, and there's possibilities for complex chemistry on this object. And so both Titan and Enceladus are recognized as potentially habitable objects, meaning that there could be life there. And we do not want to contaminate those planets with any terrestrial organisms that might have survived even more than a decade in space on the surface of the Cassini spacecraft. So that was why Cassini was deliberately crashed into Saturn at the end of its mission to make sure that it wouldn't, after it ran out of fuel, someday accidentally crash into one of these potentially habitable objects. And while we don't know whether or not Titan is habitable or not, we do have another mission planned to go to Titan. NASA is currently developing this spacecraft called Dragonfly, which is a octocopter, and it is a much, much larger flying machine than the little drone that we've seen recently doing test flights on Mars. And it's able to be much larger and have all sorts of scientific instruments because Titan has a very thick atmosphere. The air on Titan is actually very similar to the air we're all breathing right now. It's mostly nitrogen. It is missing a very key ingredient for our purposes, which is oxygen, but it's about 1.5 times the atmospheric pressure at the surface of Titan compared to what it is here on Earth. But because Titan has such a low gravitational pull compared to the Earth, it's a weaker gravity even than the moon. To get that much air pressure at the surface means the air is very dense. It's about actually 4 times denser than the air at the surface of the Earth. Couple that with a low gravity means it's very easy to fly around on Titan. In fact, it's so easy that we're trying to find a way to plan a vacation there, because if you strap some wings on your arms on Titan and make sure that you're bundled up because the temperatures are fatally cold, you could flap your arms and literally fly around on Titan under your own power and your own muscle power. So this mission is launching now, scheduled for launch in 2027, and we'll do an exploration of Titan, and we'll learn more about that moon at that time. Back at the beginning, I was showing that we used Titan to control our flight around Saturn. And when we flew by Titan, we would frequently make radar maps. So this picture is not a normal visible light picture, but a radar light image of one of the lakes. It's about the size of one of the Great Lakes. You can see there are islands, and you can see these river channels that are flowing into it. The depths of some of these lakes have been measured to be hundreds of feet deep of this methane-ethane mixture. And at the very end of the mission, as I mentioned, in order to protect those moons from contamination from any terrestrial microbes, the mission went through what was called the grand finale. This had all sorts of scientific objectives to get close-up views of the rings and the moons and the planet. And you can see here the final series of 22 orbits, which were called the Proximal Orbits, because Cassini at that time flew in between the atmosphere of Saturn and the inner edge of the rings. And during that time, it was able to make some unprecedented measurements and look at the link between the rings and the atmosphere. And on that final orbit, then it plunged into the atmosphere of Saturn and burned up. And on those 22 orbits, one of the key measurements that it made was to try to measure the mass of the rings and the distribution of material inside Saturn itself. And it did that by carefully tracking the radio signal from the spacecraft as it flew through that gap. And the gravitational pull from the rings in one direction and from Saturn in the other direction, and Saturn is a complicated, lumpy object, produced little wiggles in the spacecraft's motion, which translated into changes in the frequency of the radio signal that were able to be measured at about 1 part in a billion in accuracy, incredibly accurate measurements, which were necessary in order to be able to make a measurement of what is the mass of Saturn's rings, for example. And one of the fascinating things that came about from doing this, which is very similar to what the Juno mission is currently doing at Jupiter as its prime mission, what Cassini found at Saturn is that Saturn's interior is much more complicated than the interior of Jupiter. And what do I mean by more complicated interior? It's lumpy. It's got all sorts of asymmetric, odd distributions of matter that with those grand finale orbits, those proximal orbits, we weren't able to collect enough data to put together a nice, clean picture of what the interior of Saturn looks like. We were able to measure the mass of the rings and find out that they're lighter than we thought they were, which is part of the reason we think that they're maybe only a few tens of millions of years old. But Saturn itself is still hiding some mysteries about what's going on. It's in its interior. It's not just a nice solid planet with some clouds and an atmosphere on top. There are all sorts of interesting oscillations going on. So we've got, of those 62 moons, we have a planet-sized moon with methane weather. We have a small moon, about the size of the United Kingdom, Enceladus, that has a world-sized ocean of liquid water with geysers. The rings are evolving and changing before our eyes and have an uncertain formation that may be due to the breakup of the moon less than 100 million years ago. And so, of course, just an overview of the many things that we learned from the Saturn system, but I like to finish with this amazing mosaic of the Saturn system, where here now we can see those missing letters, the E and G rings, which are those outer two dusty translucent rings. And at the tip of the arrow, you see a little dot that I hope shows up on your screen, which is the Earth. The sun is hidden from view on the other side of Saturn in this image, but the Earth is visible through this gap in Saturn's rings in this final image. And we can, in fact, even see, if we zoom in on that dot, a little bump off to the side of it, which is light from the moon. And so there we are from a distance of 1 billion miles. And I look forward to answering any of your questions and talking more about this mission. And you can also get more information about space from our podcast that we host, Walk About the Galaxy. Be happy to talk to you about that as well. Thanks very much. I'm sorry about the mix up with the slides at the very beginning, and I'll be happy to take your questions.
Absolutely. That was awesome. Definitely check out Walk About the Galaxy. I hadn't heard about it personally until I met Josh through this whole collaboration here, and I've listened to a few episodes now, and they're fantastic. I've learned so much already just listening to the few episodes that I have, and there's roughly 2 million, I think, up there, at least a bunch.
Yes.
Plenty to learn from.
2 something, maybe not million.
Yeah, 2 something, fair enough. So we have roughly 2 million questions as well. We're not going to get through all of them, but I will ask a few of the ones that have been upvoted as a few of my favorites. And if you have any more questions, Josh, is there any way that they can maybe talk to Walk About the Galaxy podcast? Any questions we don't get
Absolutely. So Walk About the Galaxy, we've got, we're on Facebook, Instagram, Twitter, YouTube, and you can post questions to us using hashtag AskWTG, or just send us a note on Twitter or on Facebook, and we'd be happy to see those questions and talk about any of those issues on the show. Which is the inspiration for Walk About the Galaxy is Car Talk. If you remember that NPR classic. Yeah. So I don't particularly care about cars, but I love listening to those guys talk about cars and car problems. And our show is definitely not for the expert in astronomy, but meant to be entertaining and educational at the same time.
Yeah, that's awesome. That's a really cool comparison. I've also listened to Car Talk, and I don't care about cars at all, which is really interesting. So hopefully, I guess it inspired some interesting cars. So hopefully your podcast can inspire some interest in space and planetary sciences.
Okay.
All right, so let's get to some questions. The first one we got here is pretty simple, maybe. Do we know why the rings are so thin?
Yeah, the particles are colliding with each other all of the time. And so they're in a flat plane, basically the same reason that the planets in our solar system are in a plane, which is if you start with everything's got to be orbiting the object at the center. And so if those orbits are not in the same plane, objects will collide with each other. And in that collision, that'll damp down the motions that are not consistent with the average motion. So everything settles into a disk due to collisions. And because Saturn's ring particles have been collide so frequently, they're relatively densely packed, it settles into a very, very thin plane that's only the thickness of 1 or 2 particles.
That's immeasurably thin, that's crazy. Okay, we got quite a few here. This one's really great too. Is the surface structure of Enceladus an expression of the dynamics of the subsurface ocean? And are these fractures and features analogous in a way to plate tectonics here on Earth?
That's an excellent question. So the answer is partially. So some of the surface appearance of Enceladus is due to the snow coming out of those geysers raining back down onto the surface and covering up any craters or features that may have showed there. but the fractures and cracks, and there are 4 big fractures at the South Pole region, which are the source of these geysers, are probably the result of stretching and cracking from the ocean being a little bit closer to the surface at that location. And so you don't have plates, you don't have plate tectonics, but you do have forcing on the surface from that subsurface ocean, which causes cracks and migration of the ice in a sort of single global plate scale.
I saw a question earlier that was like something to the effect of why is there still a bunch of water left if it's releasing all this water into space? Is it just the amount that was already there?
So we were at Saturn for 13 years with Cassini, and we measured the rate that water ice was coming out of those cracks, and it seemed to be pretty consistent throughout the 13 years and all the measurements we made. It wasn't fluctuating by wild amounts. And if you take that amount of water ice loss and say, okay, let's say Enceladus is as old as Saturn, 4.5 billion years old, how much mass would be lost? And it turns out it would be about 10% of the mass of the original moon. So while it makes these beautiful geysers, and it could be going continuously and maybe has been going continuously for billions of years, there's not a huge amount of material in there. And so even over billions of years, it would only shrink the moon by about 10% in mass.
That's one of my favorite things about outer space is just like how absurd these numbers are, right? We can talk on the order of billions of years here and still only be talking about 10% of the mass of the moon. That's awesome. All right, so you were talking about the jostling in the rings earlier. How gentle is the jostling? If it were possible for a human to be hanging out in the rings, would they survive getting jostled? And are the moons getting altered in their orbit paths because of the jostling?
So the jostling is very gentle. The collision speeds between the ring particles in a typical region of the rings is about 1 millimeter per second. So that's really slow. If you hold your hands up, like you're going to clap, it's going to take you 5 minutes to clap at 1 millimeter per second. So it's very, very slow. So definitely if you had a nice spacesuit or a little space shuttle and you wanted to hang out in Saturn's rings, those collisions would not be dangerous at all. And that's one of the fascinating things about this whole question of whether or when they stick together, because such a gentle collision, you would assume things come together that slowly, they're going to stick. But because of the tidal pull from Saturn, they don't stick, except we have evidence that there's these occasional lucky unicorns in Saturn's rings where the particles do stick together and at least temporarily form these larger objects. So the collision speeds are low, the collisions are very gentle, even in regions where they're like stirred up and we're like, oh, that's a really dynamic, active part of the rings. It's maybe 10 or 20 centimeters per second. Siri just spoke to me there. 10 or 20 centimeters per second, which is still this fast. So it's still very gentle in even those parts of the ring system. And then I think the other part of the question was about how that jostling affects moons. Right. So if for the little moonlets within the rings, there's an odd thing that happens, which we think of gravity pulls things together. But once you get a bunch of objects interacting gravitationally, some counterintuitive things happen. And if you put a large object in Saturn's rings, you'd say, okay, that would pull everything into it. But because they're all orbiting Saturn, which is the big bully in this game, the combination of Saturn and like a moon in the rings means that the moon actually opens a gap around it. So you have fewer collisions, which is why those funny moons, the ravioli moon of Pan, opens up a gap in Saturn's rings instead of a concentration of particles around it. And those propeller looking things, which are the signature of some say, stadium-sized or skyscraper-sized moonlet in the rings are not, those propellers are not enhancements of material nearby, but they're clearing out of the material near that object due to the complicated multi-body interactions between that sort of moon and the ring particles and Saturn itself.
Amazing. All right. So you mentioned how the rings they have, especially the E-ring, right, has a lot of ice in it. I guess personal question for me.
They're all very icy, yeah.
All the rings are icy.
So
okay, that's my first
yeah,
question.
the composition of all that stuff is very icy.
But the question we got from the audience here is, does that ice melt over time, or is it pretty constant?
Well, it's very cold at Saturn. It's 10 times on average farther from the sun than the Earth. So water ice is hard as a rock at Saturn. So it can't melt, and sublimation or evaporation of the ice directly from ice into vapor is at a very, very, very slow rate. So if you weren't doing anything else, you just take an ice cube and stick it at Saturn, it's going to last for billions of years. But there are other processes that erode the rings. So they get hit by meteoroids, just as the Earth gets hit by meteoroids, and that knocks stuff off. And some of the stuff that gets knocked off can be ionized and then get tied to Saturn's magnetic field. If it's very small particles, it can be pushed around by electromagnetic forces or radiation forces. And that drives some particles out of the rings into the atmosphere of Saturn or escaping into interplanetary space. But it requires that you have this impact process from things coming in from outside, which are then hitting much, much faster than the millimeters per second or centimeters per second we were talking about. They're coming in at miles per second, shattering, vaporizing some of the ring particles directly, and those constituent, that debris that gets produced in those impacts can be lost. But one of the things that was measured when Cassini was flying through that gap between the rings and the atmosphere, it was trying to measure what's the sort of loss rate of material from the rings into the planet. We got very confusing results from that, sort of like the parable of the blind people with the elephant. One is at the legs and says it's a tree, and another one's with the trunk and says it's a snake, and another one's with the tail and says it's a rope or whatever. We have different instruments on Cassini. They each sort of measure different sizes of particles, or they measure compositions in different ways. And they all measured very different things. And a lot of those measurements were inconsistent with what we know about the bulk of the rings in terms of the composition. And they measured different rates. So we're not entirely sure how fast material is trickling out of the rings into the planet. But since the rings are less massive than we thought they might have been, and some of those rates were higher than we thought they might have been, there could be significant erosion of the rings on, certainly on the age of the solar system, and maybe on timescales of like tens to hundreds of millions of years.
Is there any indication on other planets that they might have had rings like this that have disintegrated in a similar way? Or is this kind of a Saturn exclusive thing?
That's one of the interesting questions that sort of led to a lot of the early theories about Saturn's rings. As initially we thought it's the only planet with rings, and come up with all these special reasons for why only Saturn can have rings. And then we discovered that Jupiter and Uranus and Neptune all have rings around them at the present time. Now they're very different looking than Saturn, and they're much smaller systems than Saturn's. But Uranus and Neptune are much smaller planets than Saturn, and Uranus has a whole family of interesting rings around it, which seem like they were created by shattering of moons. Each individual ring looks like it's the debris from the breakup of a small sort of pan-sized, that's the ravioli moon. Break up a moon like pan, and you'll make a narrow ring around the planet. And so it's possible that those planets had very different looking ring systems 100 million years ago or 1 billion years ago. And it's possible even that Saturn maybe had a big ring system 2 billion years ago, and it's long gone. And what we're looking at now is a very different ring system than what existed over the history of the solar system. And I think it's worth mentioning that even the Earth had a ring at one time. It didn't last very long because of the nature of the part of the solar system we live in, but it's an impact onto the Earth when it was first forming that created the moon. And it's not an impact that like comes in and knocks off a chunk and then the moon is that chunk. It's an impact that basically obliterates the outer part of the Earth and sends a huge amount of material into orbit around what's left of the Earth. And that material would have made a big, broad ring of material around the Earth. And a lot of that material fell back down onto the Earth, but some of that material moved outwards, and some of that outward moving material collided with it itself, had collisions amongst those particles, which ended up forming the moon as the largest leftover piece of that. So yeah, all planets have an opportunity to have rings. The formation mechanisms, the most obvious one is shatter a moon. And in our solar system, only Mercury and Venus don't have moons at the moment.
That's pretty amazing then that humans have not been around very long, but we get to exist in a time where, you know, maybe it's only a 200 million year sliver of time where Saturn's rings are as big and awesome as they are, and we get to watch them actively change over that time. We were born 100 million years, you know, earlier, we wouldn't see the rings at all like they are.
Right. But we would, yeah, but then it makes you wonder what crazy things might we have seen at that time that we may never be able to know about.
I mean, the Saturnian alien megastructure, of course.
Right, yes.
All right, let's get back to the audience questions, not just nerd out about my own. Let's see, we got one here. How does the presence of a moon open a gap in the rings that extends around the entire ring structure? Why aren't these gaps more local phenomena?
That's an excellent question. And as you saw, we saw some examples of those localized gaps, just like what the person asking the question would predict. Those are the propeller objects. The propeller objects are like localized gaps. They don't go all the way around. And they're produced by small moons, few hundred meters across, something like that. As the mass of the object gets bigger, the mass of the moon gets bigger, its perturbations on the surrounding material get larger. So basically what happens is, we know nature abhors a vacuum. It's the common expression. And that applies to a ring system as well. Rings, bunch of particles, and the particles bump into each other. And if you bump into a particle on your left, but not into one on your right, you're going to move into the right. So you'll fill in a gap to the right. So you would expect gaps to fill in because the particles on either edge of the gap are getting jostled only on one side, which would cause them to fill in. And there's a time scale for that filling in to occur. And at the same time, the moon's complicated three-body interaction with those particles pushes them away. The bigger the moon is, the farther away it pushes them, which makes it take longer for the particles to fill the gap back in. And because the particles are not orbiting all at the same speed, the moon is constantly clearing that gap. So if you're a ring particle at the edge of a gap, you see the moon go by every so often. And so it's constantly coming by and giving you a little nudge and pushing you out of the gap. And the bigger it is, the bigger that nudge and the harder and longer it would take for those particles to fill that gap back in. So these moons are called, the same process happens with moons on either side of a ring. They hold the ring particles together and prevent that ring from spreading out. We call those moons shepherd moons because their gravity is shepherding the ring particles and keeping them confined. If you put it in the rings, it shepherds them away from itself.
Awesome. Yeah, that makes a lot of sense. What accounts for the development of the ring-like structures on Pan? You talked a little bit about it, but you could go a little more in detail. And additionally, why do each of Saturn's moons develop so differently?
So Pan, again, is this, I call it the ravioli moon. It has this funny equatorial ridge of material. And I've just given this beautiful explanation about how Pan opens a gap and keeps all the ring particles away from it. At the same time, you didn't see it in any of the images I showed, but there is some material in that gap where Pan orbits. And smaller particles, like really tiny, dust size or pebble sized and smaller particles, have an easier time moving around than the bigger particles. And so there's some material that leaks into that system. And there, in some images, we can actually see a little tiny ringlet that's discontinuous in that gap. And so as Pan is going through there and clearing out its space, which is called the Encke gap, it runs into some of these particles, and those particles stick to its equator and build up that ridge. What I find fascinating about that picture is that ridge has sides, like it's not circular. It seems to be hexagonal. There are also a bunch of grooves on the top of the ravioli, like if you take your fork to let the steam come out or whatever, there are several grooves on the top. And it looks like there are sets of grooves that are offset from each other by 60 degrees, which is also a hexagonal pattern. So there's some interesting, complicated dynamics that's the subject of ongoing research to try to understand what's going on in there. Yeah, it's basically picking up stray ring particles. I think the other question was about the different evolution of these moons. They're, it's nature versus nurture, maybe. It's that they grow up in different environments. So if you grow up close to the rings, you're going to be accreting material like that. Farther out, you may be affected by these tidal interactions with other moons, which is what's happened with Enceladus. The contrast between Enceladus and Mimas. Mimas is the Death Star moon, which is a bunch of craters. Enceladus is its next door neighbor, about the same size, completely different appearance, completely different history. And it just has to do with being in an environment where it's getting squeezed and stretched so that it heats up the interior and melts water in its interior, which then has to go someplace.
Awesome. We got time for a couple more questions. One of them here, I think, when you showed me the photo of Cassini, I was kind of surprised by how big it was, right? Because I've always known about Cassini, but I kind of just pictured it smaller for some reason. I guess Earth-based satellites are normally smaller.
Yeah.
But I often like visualize how amazing it is that we've done this at all, right? Because we pick up rocks and metal out of the ground and we put them together in a special way that we launch it into this tiny dot in the sky that we can barely see, and then we pilot it between the rings and the planet of that tiny dot. It's incredible. So just all of these missions are awesome. Cassini, I'm sure is it would you say it's your favorite space mission so far?
I mean, come on, it has to.
It has
I have such, it's, as I said at the beginning, even though I had a slideshow failure there, it's the mission of a lifetime, and it really was the mission of a lifetime for me. And so yes, it has a special place in my heart. But just talking about like the precision of things, humanity landed the Huygens probe on a dot, orbiting a dot in the sky. And not only that, but we landed it like in the county on that dot where we were aiming, So it's just a remarkable accomplishment.
At that distance too, because we landed Perseverance pretty close to where we wanted to. But Mars is like, I could throw a rock and basically hit Mars. It's right there. Saturn is 1 billion miles away. And like you said, we're not even hitting the planet. We're hitting the moon surrounding the planet. And then we're using that moon to pilot our spacecraft. Okay, definitely. But the real question here is, if you could develop another mission going to Saturn, what aspects would you want to focus on?
I'm very excited about the Dragonfly mission that I mentioned, which is going to be flying around. I would love to like see an air, like a dirigible on Titan, because then you could do global exploration of that moon Dragonfly is going to be flying around, but fairly locally. It's not going to be traveling huge distances. But you could have an air machine, that could stay afloat in Titan's atmosphere for a long time. It would be very interesting to get a really better taste of the material in Enceladus's oceans and find out, is there enough ingredients for life inside that little tiny moon? So that would be a very exciting mission, and people have developed strategies for that sort of mission. I have, my own affinity for Saturn's rings, and it would be cool to see a ring skimmer, which would be a spacecraft that would basically fly over the rings. And that's, for dynamical reasons, not an easy thing to do. For the same reason that the rings are all in one plane, that spacecraft would want to be down in the plane as well. But you can do some tricks and use some fuel to make that happen. And it would be really interesting to see these particles. We've never seen a ring particle. I said, oh, it's like a snowball. But we've never seen one.
Right.
And we've never seen those collisions actually taking place. So that would be a very exciting mission. And then for the planet itself, it would be very interesting to send a probe, multiple probes really, into Saturn. I didn't have time to show, but there's this tremendous hurricane at the North Pole of Saturn. It has storms that crop up every 30 years or so that are sort of global scale. We don't totally understand why that's the frequency for those storms. So there's, as always, the missions raise a number of new questions in addition to answering old ones.
Yeah, of course, right. So at the end here, we can focus a little bit on that the Dragonfly mission going to Titan, is that upcoming mission, which I think is super exciting. Who is leading that exactly? Is it for sure happening? Who's leading it?
It is. So, well, I mean, yes, it's selected and it goes through periodic reviews, but it has been selected for flight and is being developed for flight and launch in 2027. The principal investigator is a colleague from the Cassini mission. Her name is Elizabeth Turtle. She's at Johns Hopkins, and she was on the imaging team of Cassini. So she's the principal investigator of that mission. Awesome. And yeah, I saw a question about, there's all sorts of natural gas. Methane is a dangerous flammable substance here on Earth, but it's only flammable if you've got oxygen to burn it. And there's no oxygen available on Titan, so we don't need to worry about any conflagrations of that sort there.
That's good. Yeah, one less thing to worry about. We have plenty to worry about in just getting it there and landing it.
Right.
All right, well, I think that's all the time for the questions that we have today, but if you have any more, I know there's a bunch that we didn't get a chance to get to. Definitely make sure you're checking out the socials for Walkabout the Galaxy, because obviously Josh has a lot of them. You'd love to talk more about them. But thank you all so much for attending. I'm glad that we got to have this talk. I certainly learned a lot. I think that was super exciting. Like I said, make sure you're checking out the Planet Pioneers exhibit here at the Science Center. It's going until May 9th, and so you don't have a whole lot of time, but a little bit to make sure you're getting over here. But you can, land a rocket, which I've never been able to do before successfully, but lots of really fun and awesome things to do here. Not just for kids, for all age ranges, especially adults. You can have a lot of fun in that exhibit and a couple of hours really interacting with all the different pieces. And then we also have another talk just like this one by a colleague, Dr. Addie Dove is going to be doing a talk for this speaker series next week. That's called Extreme Explorers, Challenges of Exploring Our Planetary Neighbors. That's happening on May 4th at the same time from 12 to 1 p.m. But thank you to UCF and everyone who helped put the series together. Thank you to Josh for giving our talk today, and I'll see you guys later.